All right, so we're gonna move on to next chapter, chapter 16. So we're gonna learn about some reactions that we can do with some the benzene ring or aromatic compounds over here. So the chapter 16 usually talks about the electrophilic aromatic substitution. So basically what it means that we have a aromatic ring structure over here. Looks like this. But if you don't guys see this on this structure, but we all know there will be implied hydrogen on here, or on these carbons in the aromatic ring structure. Okay. So whenever you have a aromatic ring with some electrophile, which is normally you guys remember this, right? Electrophile usually positively charged, so they can look for something electron-rich place, so it can be more stable. So this, if you have some electrophile here with the aromatic ring, they might do the substitution reaction, which is you're just gonna replace this one here. So you're gonna have this type of structure over here. So it's replaced by this one. So you're gonna have a replacement over there. Okay. So this is something we're gonna discuss in this chapter most of the time. And so if that is happening, there are several things we can do. So if you replace this one, this hydrogen, with some maybe this hydrogen to maybe halogen. So this is what we call, so we can replace this one as like next element, the halogen element. So this is become really aromatic halogenations. So aromatic halogenation. It's literally what it says. Okay, so this is the one thing we can do. We actually discussed this one today. And then if you replace this one with the hydroxy groups, okay? So like some OH groups over here. So this is the hydroxy group, so we call this hydroxylation. Okay. So when we have a replacement of the hydrogen to the hydroxy group, we call this hydroxylation over here. If we change this one to NO2, okay, over here, nitric group here, and we're gonna call this nitration. It's nitration over here. Okay, and then when we change this one to this group over here, we can name this one as the sulfonation. Okay, so this is something you can do. There are several other things you can do. Is when you put some AC groups, this is what we call AC group. So it's an acylation. So the acylation, this is acylation. This is alkylation. So those two will actually we're gonna do in the lab soon, from this week and the next week. So this is also a good example of nucleophilic aromatic substitution. So I think, yeah, that's it. Yeah. Okay. Yeah. So whenever we do this, we can call this electrophilic aromatic substitution. So we're gonna start with the halogenation today, but before we go into the halogenation, I just wanna give you some review. Okay. So if you have this one over here, right? This is the review. Okay, this is the review. I'm going to do this to compare. Okay, compare to what we're gonna do now. Okay. So if you have this one, this is just a regular alkene compound, right? Alkene with the double bond and somewhere in 2 carbons, and then obviously the electrons in the p or pi bonds will behave like looking for something that is the positive over here. So they can do here. So they can do this one attack. So it will become here, and you're going to see carbocation over here, because you see this is attack here, and this now will attack something that is positive. This will behave like a nucleophile again, and then they actually put on here. So you're gonna have this. You guys remember this, right? This is what we did in Orgo 1. This is a kind of quick review because we want to compare this one to our other example of aromatic halogenation. So try to keep this in your mind. This is a quick review from the Orgo 1. Okay. Try to put this in your mind. Okay. All right. So this one is kind of special, and we also need this substitution. Okay. And we're going to talk about why is it has to be substitution here. So when we think about halogenation, aromatic halogenation, maybe you want to do aromatic bromination. Okay. When I do aromatic bromination, the problem is here. The problem here is your aromatic ring, your benzene here, is very stable, right? You guys remember it's very stable, right? Because there's conjugation and everything on the ring structure. It makes very stable. So if it's stable, it means it's less reactive. Because it's stable, why would they want to go into the chemical reactions, right? There. So to make this brominated, you need to have a special catalyst, which is the iron 3 bromide. So we're gonna have help from the catalyst to make this unlikely happening reaction to proceed in the forward reactions. Okay. So whenever you have, does it make sense? Because this is very stable, right? So it doesn't have to be brominated because it's already stable. Why would they want to go over bromination and here? So anyway, there's I'll tell you in the process. Okay. So if we do this one, I happen to this one here. So this is bromine over here, right? And this we have iron 3 bromide. Okay. We have iron 3 bromide here, and then it goes to here. Okay. So this pair of electron goes to here, so that makes iron tetrabromide negative. Okay. Because they now have a 4, it's negative. Makes sense, right? Negative. And this will become, because they all go to here, right? So it now lost the 1 electron here, right? 7, but only 6 here now. Okay? So that will become positive, and this will be picked up by this one. Okay. So whenever you have this one over here, does it make sense, right? We good? Okay. So if that happens to here, you're going to see this one over here. Okay. So we have this one. This is picked up by this one, right? So this is gold, and also we have hydrogen over here. Okay. And then obviously, when it's picked up by this one, as we already saw from the alkene, this is positive charge. Because if you look at this one over here, this is a 1, 2, 3, right? This carbon only has 1, 2, 3, because the double bond is gone now. Okay, so pair of electron used for making bond to this bromine cation over here, right? So then this is carbocation over here, and the thing is that the alytic position or conjugation we learned in the previous chapter. It can move, right? It can move, right? See this move? So you can have this one, and also this one. Okay. Not here. So it moves to here, here, and then it can also move to here, right? So so these are three are possible. They go back and forth because of this bond can move. You remember this one, right? From the conjugate compound. You guys remember this, right? Okay. So if that is happening, if I redraw this one in the one, so this is where you can have a carbocation or here or here. So if you redraw this one, it looks like this. Here, okay. So gives those three. So this does the positive charge and this localized electron can be delocalized. Does it make sense? Because this is the way we can move the double bond around with the carbocation. So we have three possible case. You can put it in this way, and this delocalized positive charge with the cyclohexanol like a compound. We call this uranium ion. So we'll show you some uranium ion form because of the three possible scenario you can do with the carbocation with the bromination in a process of the aromatic bromination. You're going to have some uranium ion formation because it could be somewhere in here except this region here. So it's kind of partially delocalized in a structure. Okay? But this is not so important, but I just want you to know there will be carbocation here, okay? Okay, so then, so you now to double bond is gone, right? And this is now here, over here, right? Now we're here, okay? Now we're here, and then you have this one over here, right? And the charge, and one of the bromine in here will grab this one, okay? The hydrogen. So this can go in here. This bond can go in here to make a double bond again. So this hydrogen is picked up by one of the bromine here. So it becomes bromic acid here plus ion now. Okay, 3 bromine. Okay, once again. So the now you have a bromination on this aromatic ring by just substituting your hydrogen to this one. Okay, and as you can see, the catalyst stayed in the same form. So we can call it zero catalyst. Okay, so there are a few things I want to tell you about this one. Is why it has to be in this special way. Once again, it's because of the stability, very strong stability of the aromatic compounds. So if you look at the diagram, energy diagram here, it actually stayed in a very low position in the energy diagram because it's very stable. Very stable, the benzene ring is very low here. So most of the alkene or other compounds may stay in here, much higher position than stable aromatic compounds. So they goes all like this in the first step, okay? But this one will go up to very high, like a what can I say, bump, meaning your activation energy. Okay? So it requires a lot of activation energy to overcome. So this is why we need to have the catalyst to make it happen more smoothly. Okay? So if that is happening over here, whenever you get to the carbocation form over here, maybe somewhere, so you can have some intermediate over here, right? So whenever you have a reaction intermediate over here, which is this one, once again. Okay, this one over here. The thing is that we'll do the substitution, not the addition, because when you do the addition over here, it's what it looks like. Okay? But when we do the substitution, they got this. Okay, so this is what we saw. Oh, this is two. So this is what we saw as a substitution. Okay, and this is when they have possible addition from there. Okay, over here. Okay. So this is not going to happen. This is what we saw from the reactions. Okay, so this is what happened. This is possible, but it's not going to happen. Actually, it's a possible scenario, but it's not possible. Actually. So this is not happening. And then, as you know, if you do the bromination on the alkene compound, you probably saw even the alkyne compound. It has two bromines attached to it because it's bromination. But in this case, this will not happen, but this will happen. Can you guys guess why? Oh no. Oh. So the thing is this one. Like I said, the compounds always going to do reaction when they can be stabilized. This is what we saw over here. Okay, so this is the one reason over here. But for this one, when you go for another further bromination here, the biggest problem for this one is the aromaticity. So in here, is aromatic or not? By 4n plus 2 rule, is aromatic or right? No, right? This is only 4 pi electrons, there's 6, right? So this is why when they go further on the bromination here, they will be very high in energy position. So this is very unlikely to happen because it actually breaks the aromaticity of the compounds in the process. But this one still keep the aromaticity, but still you can do the bromination, and overall this reaction become exergonic reaction, which is more stable at the end and the product form. But this is not. Because of the aromaticity, you lose during the process. So this is why you need to have, in the first place, very special catalyst to make this big hurdle tube jump over, to make it lower and smoother. And then when you go for the substitution, they'll make more stable products instead of this unstable possible outcome. So this is what we observe all the time from aromatic bromination, which will be only substitution but not addition. So this is the major difference between just conjugate alkene, like diene kind of compounds, than ones in the aromatic compounds. Okay. Kind of makes sense? Okay. All right, so the okay, so if there's an aromatic, so we just went over the aromatic bromination. How about the other aromatic halogenation? Okay. So the fluorination, when I fluorinate the compounds, as you know, fluorine is very unstable because it's very small. If you look at the periodic table, and very highly electronegative. So we don't do normal substitution, but they use a special compounds to use. Okay, so you're gonna have a very special the compounds. We named this one as it's a fluoro TEDA boron fluoride. Okay, so this is the kind of a way to make it reaction more in a safer and more stable way. So whenever you do this one, have fluorination on the aromatic compounds over here. It's just because of this kind of this fluorine is very reactive. This is a much safer way to actually here. So whenever you do this type of reactions here, you're going to have possible other locations. This is let's do 1, 2. I'm sorry. I'm going to draw it right here. This is also possible. So you can start with the toluene. Okay, toluene over here, and this is your base, right? So this will be. Do you guys remember this? This position will be orthofluoro. Okay. Toluene, and this is para. This is a para P. Fluoro toluene. So there's two possible fluorination products. It could be over here, but they'll still be the same thing anyway. That's why we're doing it too. Here, but these two are the same, right? So we want to. Okay. So this is kind of one exception because of the fluorine is kind of too reactive. But as you already saw for the bromination, for chlorine, it's pretty much the same. What we just saw from the bromination. So when you have this one over here, you just need to do chlorine and also iron 3 chloride. That's it. It's the same. So you're going to have it's just same mechanism we saw with the catalyst with the chlorine. So bromination and chlorination is the same similar process you can do. So this is just that. Okay. Like I said, fluorine was a bit of a exceptional way. Okay. So this is kind of special because we have some compounds. So we have some special compounds that looks like this, also go through this aromatic chlorination. This is Claritin. Do you guys know what this is, Claritin? This is anti-allergic medicine. So this is indeed very useful in medicinal chemistry. You want to make some medicine, this compound, because a lot of products usually has an aromatic ring because the sterility it gives to the compound. And this is one way we can do the practical way. Okay? But it's very similar to the bromination. So I'll just move on. So the last one is the iodine. Okay. So the iodination will be quite similar, but a little bit slightly different because you're gonna do it with the copper 2 chloride. So if you do the copper 2 chloride, okay, you can do copper 2 chloride over here. Here's the one thing you can do. This copper 2 iodine atomic molecule over here. This means you have a copper 2 plus 2 Ca minus over here, right? So we're gonna use a 2. Sulfuric ion over here, copper 2 cation. And then you can actually do 2 iodine cation here with the 2 copper plus 1. So in this case, this will now behave like an electrophile. and then this will be grabbed by this, okay, over here, and then we'll do the aromatic substitution, electrophilic substitution. Like this. So it's very similar. It's only difference. It's only different when you. Oh, I'm sorry. So it's the same. And then when we have a. So this can be treated with the base and picked up and goes to. Yeah. I just kind of forgot about this. Is the same process anyway, but as you can see, it's just simply another type of electrophilic aromatic substitution. So once you get to here, it's picked up by base and goes to the double bond again. So you have iodination here, which is quite similar but just slightly different products types of way. So the this is one way. Okay. Does it make sense? So the halogenation beside the iodine and the fluorine is pretty much similar, but it only slightly different from how they get to the electrophile to grab from the pi electrons. And then once they do it, just this, the electron can be picked up by the base, so they can do an original double bond. So there can be just a substitution, but not addition, which is once again much more stable form than just doing addition or other type of reactions. All right. Does it make sense? Okay. So there's a couple more things I want to go over today. Is the first one is nitration. So once again, we're gonna make this one. Okay, we're gonna make this one over here. So this one, the nitration, you're gonna do with the this way. So you're gonna have a nitric acid here, and you're also going to use the sulfuric acid here as well. Okay, so you're going to sulfuric acid is just kind of that give us the cation. This is only thing. You can say hydrogen cation. It doesn't matter. It's just different definition anyway. So this is a kind of a proton donor. This is what we're actually going to do something about here as an electrophile. So what happened to this one? So if you have, I hope that you guys remember this one. This is nitric acid here. Because of the double bond can be 2, so it has a central positive charge because of that. Okay, so this is why it has the central cation in the center with the nitrogen. But the electrons are shared in these two. The one picked up by hydrogens, they can behave like an acid. So it's a very strong acid here. So whenever you do this one over here, as you can see, this will give us a lot of numbers of hydrogen cation. Okay? So this is picked up by here. Okay? So we'll make what? I hope you guys remember this from the Orgo 1, 2. That makes really, really good leaving groups. You can remember which is water. Okay? So you have a positive charge, okay, and yeah. So if you do this one over here, this is a positive charge, right? Because this is 1, 2, 3, 4, 5. Okay. So now it has lose one of the lone pair to pick up the protons here. So this is a positive charge, which is really good leaving groups. So we'll leave, okay? But whenever it leaves, leave in this way. So there's a 3 lone pair because it's a negatively charged oxygen right here, right? 1, 2, 3, 4, 5, 6, 7. So this one of the lone pair goes to here, and then this goes to lead to here. Okay. So now it has a pair of electron here, so it become water, right? Because it's a 2 lone pair now, and the 2 hydrogen here, so it'll be 6. So water. And this will become, so there'll be double bond over here, right? So this is now water. It left already. And this one becomes this, okay? Because we have 2 double bond now. Okay? So it becomes nitronium ion. Okay, it's a positive charge. Makes sense, right? Good. So if that is the case, what you guys can think of? This is also a good example of what? Electrify now, right? Okay. So this will be now by this one. Okay, because it's now good electrophile. So when you pick up by this one, this is gone, right? This is gone. And now go to the nitrogen positive. Okay, here. What's the problem here? What's the problem here? So it could be the electron is donated here. This is the over there, right? The problem here is, can you guys see any problem? Can you guys maybe think about this one real quick? So if this is a positive charge, now it grabbed by the pair of electrons in the pi electrons on here. So it's now neutral, which is perfect. But because of the structure, do you see the two double bonds over here and one single bond, which is very unstable because the nitrogen is very small. If you look at the nitrogen, it's the second period. This is very small. So a very small element can't do the double bond in the angle. No, it's impossible. So what they do is whenever they do this one, goes to back here. So they can keep only one double bond there. Okay, makes sense, right? So this will become positive charge again, and this is negative charge. Okay, so you can more stable this way, even though they carry the charge plus and minus here, which makes somewhat unstable, but better than this one. Okay, so this is the second best they choose. Oh, yeah. So then here you have a hydrogen as well here. This will be picked up by water. You remember this water here, right? So water picks it up and goes there. Okay, so now it goes to. Okay, and what? Cation. So water picked up the hydrogen, become hydrogen cation. So this is nitration. So if you draw this one carefully, actually, this is actually what it looks like. But in total, it's it's neutral plus or minus. So this is the nitration. So it gets a lot of the presence of the cation. Nitrogen can be the nitronium ion, which is a positive charge. So it can be a very good electrophile, which we can use it for substitution reactions. No, it's not hallucination, but nitration. So you can pick up the electrophile in nitronium ion. So they can just do the pick up the hydrogen on that position from the water, which is kind of behave like a base in here, and try to put back into the original aromatic city, which is more stable. So that's why they want to do in this way, so they can still keep the aromatic city, which makes the very stable products, which is more favored way to they want to proceed. Makes sense, right? So the actually I'll stop here. So I'll move on to the next one, but I'll try to do this one again, maybe on Wednesday. But I don't want to do a lot just one day because we have plenty of time. So we'll do this again on Wednesday and the other ones. All right, thank you guys.